two more devices, two new devices, which belong to the category of field effect transistors. Okay, one is the plain field effect transistor, and the other one is called as a MOSFET. Just let me share the screen. Okay, is the OneNote page visible to all of you?
Yes, sir.
Okay. So the very first thing that we would see or notice is that the field effect transistor, FET for short, is a voltage controlled device. Now, what we were seeing in bipolar junction transistor was that we were essentially applying a base current, for example, okay, and then there was a change in the collector current, and correspondingly things were happening. So bipolar junction device is a current control device. This is the major difference. So BJT is a current control device, whereas field effect transistor is a voltage control device. Simply means that we require virtually no input bias current or even signal current, as a matter of fact. So there is no input current at all. So input current is almost zero. This gives a wonderful, let us say, characteristic to this device. And what is that? Whenever you would measure the input resistance, what was the way in which you did that? Input voltage Vi, so Ri is Vi by the input current. In this case, it was the base current, for example. Okay, so if this base current or input current itself is zero, what can you say about Ri? In field effect device, if input current itself is zero, what would you say about Ri?
So it will be infinite.
Ri is almost infinite. Practically, it is very, very high. And whenever we think about devices, we always have to make sure one thing, that the input resistance is as high as possible. That is a good device, ideal device, let us say. Okay. So now we have two flavors of this field effect transistor. One is called as the junction field effect transistor, which we will start discussing immediately, and the other one is called as a MOSFET. We'll see that in the later part of the unit. Okay, so let us start with the junction, or JFET for short, junction field effect transistor. So let us first of all see how it is constructed. So there are again two types of JFETs. You have the N channel JFET and the P channel effect JFET. Okay, let us see the N channel JFET. Is the screen visible to all of you still?
Yes, sir.
Okay. Please tell me if it gets frozen somehow. So please tell me that.
Yes, sir.
Okay. So let us look at the construction. So essentially, what you have is an N channel. Okay. So this is an N channel. N channel means N type semiconductor. So this is N type semiconductor. Then we have two P channel semiconductors attached to it like this. Okay. So this is P type. All right. So if you look at the terminals now, this is one terminal, this is another terminal, and this is one terminal, this is another terminal. Most of the times, these two terminals are internally short circuited. They are connected, so they are one and the same. They are called as the gates. So this is gate. This is called as drain. And this is called as source. Okay. When you want to connect it externally, you would almost always have this connected to a positive terminal. This you have connected to the ground. And this is where you would apply the inputs of the input. I'll just put it this way. So it will be like this. Gate will be equivalent to base. Source will be equivalent to, yes, anyone? The emitter, and the drain would be equivalent to collector. Okay? Hello, guys, am I audible?
Yes, sir.
So a piece of N-type material, which we call as channel. So this actually is going to be called as a channel. N channel is connected, is attached. We have two smaller pieces of P-type material attached to this N channel. Okay. So we have this kind of structure for the field effect. Now, when I am not connecting any voltage, let us see what the situation is. Okay. If I simply say that this is the N channel, okay, then you have the P channel connected like this. So this is N, this is P. So as soon as you have the N and the P, what kind of, what do you think will happen? This is simply a PN junction, no?
Yes, sir.
This is a PN junction. So when you attach, metallurgically connect P and N, what will happen?
So a potential barrier will be generated.
Exactly. So you have, but because of what? Because of the depletion region. So you'll be
Yes, sir.
having depletion regions being created. Okay. So you'll have depletion region being created. Here. So this is the depletion region in P type, both sides. Let me get a color. And you have depletion region being created here also. So we have the existence of the depletion region. Okay. Now this is true when we don't have any voltage connected to the device. When we connect the voltage to the gate as well as to the drain and the voltage between drain and source, things are going to change a little bit. So when the gate is biased negative with respect to source, so let us try to do that. Okay. So let us try to connect this in such a way that it is negative with respect to the source. This is the source terminal, this is the gate terminal. Similarly, I have. So what are we doing here? Which type of bias are we providing to this EN junction? What type of bias are we creating? So this is
So
VG.
reverse bias.
It is a reverse bias, correct? So in case of reverse bias, what will happen? What will happen to the depletion region?
So it will increase.
Depletion region width will increase. Very good. So what we have essentially is that the depletion region will increase. Something like this will happen. Okay. Now if I go on increasing the reverse bias, what will happen? So if I increase the reverse bias still further, what will happen?
एक पॉइंट आएगा जो दोनों साइड के डिप्लीशन रीजन कंबाइन हो जाएंगे.
Yes, exactly. So it will increase to such an extent where both the depletion regions will touch each other. They go on increasing and ultimately they will touch each other. Okay. Now, why do you see that the depletion region extends more in the N-type region or N channel? Because N is more lightly doped. More lightly doped than the P-type gates. Remember this. That is the reason why you see that there is an unequal distribution of the depletion region. Okay. So the channel gets narrowed down and ultimately its resistance will also increase. So if I connect some kind of a source here, some kind of a supply over here, okay, and if there is a drain current which earlier was flowing, now why will the drain current flow in the first place? Okay, let us do away with this and then I will explain. See, this is an N-type semiconductor. So what is an N-type semiconductor? Actually, it is essentially some type of a conductor which has got some resistance, right? Higher resistance as compared to the conductor. So when you connect a voltage across that piece of semiconductor, obviously the current is going to flow. Are you able to understand this? Guys?
सर ये पॉइंट समझ में नहीं आया.
अरे मैं सेमीकंडक्टर ले लूं, एक पीस ऑफ सेमीकंडक्टर if I take, If I take
Yes,
a
sir.
piece of semiconductor and if I apply voltage across it, obviously some current will flow na, through the
Yes,
semiconductor.
sir.
So current is going to flow. तो यही करंट है जो ये करंट ड्रेन करंट. This is going to flow through the channel, no problem with that. Okay.
Yes, sir.
But as I go
Yes,
on
sir.
increasing this bias, negative bias, and as we have seen that the channel width goes on decreasing. तो ये width का क्या हो रहा है? ये width कम हो रहा है ना?
Yes, sir.
Width कम हो रहा है तो how will it reflect in the form of resistance?
Sir, resistance will increase.
Resistance will increase, obviously. So channel resistance increases and drain current. What will happen to drain current now if channel resistance increases?
Sir, it will decrease.
It will.
सर आपकी वॉइस चली गई.
Yes, sir.
Yeah, am I still audible?
Yes, sir.
The drain channel resistance increases with increase in VGS. Therefore, drain current decreases. Simple, eh? And ultimately, if VGS is large enough, that is the negative bias is large enough, the channel is going to be cut off. Okay? Where ID is completely zero in that case because there is no channel existing anymore. So what can you see from here? A very simple construction, a very simple mechanism. What is that? The voltage over here, the voltage between gate and source controls the drain current. Can I say like that?
Yes, sir.
So voltage between drain current, gate and source controls drain current. Look at this statement. Very, very important. And that is the reason why we call this as the voltage controlled device. Acha, what will be the current flowing inside the gate terminal? What will be the current flowing in? I mean, what will be this current?
So reverse saturation current.
Exactly. So it's going to be a very, very small current. It's going to be a very, very small current, which is equal to the reverse saturation current because PN junction over here is reverse bias. So we can say that very, very small current, almost zero current is flowing. So this is essentially not a current controlled device, but a voltage controlled device. Is that clear to all of you?
Yes, sir.
So is the working mechanism clear to all of you? Any doubts, any questions here? Very, very important.
No, sir.
If there are any doubts, any questions, please raise it right now. So why it is called as, so why it is called as field effect? So the name actually derives from the fact that the depletion region in this channel, which are a result of what? The electric field at the reverse biased gate channel junctions. So why we call it as field effect? Because the depletion region in the channel is a result of the electric field. This is important. Where is that electric field? At the reverse biased gate channel junction. This is important. So who is responsible for creating this depletion region? It is the electric field at the reverse bias gate channel. And that we are controlling, and that actually controls rather the drain current. Okay. Also, one important thing for you to observe over here is that the drain current is made up of which type of charge carrier? At any given time, the drain current is made up of which type of carrier? Which are the majority charge carriers here in N type?
So electrons.
They are the electrons. Okay. So we have majority charge carriers at electrons. So naturally, whatever is the current flowing is because of these electrons. Are there any holes involved? There may be a few, very few holes. And as we have said that N channel is more lightly doped. So holes are even less. So we can say that there are almost no holes in this N channel region or this N channel. Okay?
Yes, sir.
Yes or no? And so the current, the drain current is composed of only what? Electrons in this case. So we call it as a unipolar device. Why were we calling the transistor, this particular transistor which we have seen in the last session, we are calling that as bipolar junction device, no? We are calling that as bipolar junction device. Why?
Yes, sir.
Because in BJT or bipolar device, the currents compose both of electrons plus holes. Here we have only one type. If it is N channel, it is only electrons. That is for N channel, and or other holes for P channel device. So at a given time, only one type of charge carriers are responsible for the drain current. That is the reason why it is called as a unipolar device as compared to the bipolar device that we have already seen. Is it clear?
Yes, sir.
Okay. Let us see the schematic symbol. For field effect transistor. So there are various symbols. Unfortunately, this causes some kind of confusion, but most of the times it will be shown like this. So this is N channel device, N channel JFET. Please don't get confused. This is your gate, this is your drain, and this is your source. Okay. Similarly, you may have different, for P channel, you have something like this. So again, you have this as the gate, this as the drain, the source. Now there are alternate symbols also. This is P channel. Some alternate symbols also exist. Let us have a look at it, which I think is more intuitive. You don't have to bother about anything else. It's nearly same. So this is for N channel, and this is for P channel. Again, this is gate, drain, source, gate, source, and drain. So are the symbols clear to all of you?
Yes, sir.
Okay. Let us go and see now the characteristics of N-channel JFET. Okay. So characteristics. Of N-channel JFET. I'll have to draw a figure for that because this requires certain explanation. Okay, am I still audible?
Yes, sir.
Okay, there seems to be a call drop here. So I'll just draw a large channel like this. Another channel like this. Then I will connect, let us say, plus VD here, so that the drain current starts flowing. First of all, what I will do is I will simply make VGS equal to 0. Means that there is no voltage difference between the source terminal and the gate. So this is your gate. There is no reverse bias right now. And of course, there is some built-in reverse bias, of course, there. So this is the source. This is the drain. Okay. Now let us have a look at the depletion regions which are created over there. So this is the depletion region on this side, depletion region on this side, and we have, as we have seen, there is depletion region which extends more into the. Now it is going to have a peculiar shape like this. Let us see why this is there. Slightly bulging on the upper side and then going like this. Okay, there is a reason for that. We are going to study inside. So the drain current will flow. All right. Okay, up to this point. So what we
Yes, sir.
have is gate is connected directly to the source terminal, as we have already said. Now due to drain voltage VD, please remember that we are applying VD over here. We are applying VD. Drain current will start flowing. Okay. So drain current will start flowing like this. Okay. I'll show it with a dot. Fine. Now this N-type material, this is N-type, we already know that now. This is N-type, this is P-type. So this N-type material is resistive, right? There will be some resistance of this channel. You know already that. Okay? Yes or no?
Yes, sir.
So now consider these points over here. Okay, consider this as, let us say, point A. Consider here some arbitrary point B, and here as, let us say, point C. I'm just marking the point, that's all. So this is point A, this is point B, and this is point C. This is very, very important concept. Now, as I go along this channel, what is going to happen? What is going to happen? As if you are having a resistor like this. So this is your drain, this is your source, and we are tapping at various points A, B, and C. So as current flows, what can you say about voltage at A, voltage at B, and voltage at C? Will they be equal?
No, sir. It will decrease.
Yes, they will. They will have drops. So obviously, VA is going to be greater than VB, which is greater than VC. Okay.
Yes, sir.
So if you measure voltage at A, it will be higher. At B, it will be lower. C, it will be still lower.
Yes, sir.
Okay, na? So what will happen? I mean, what can we say about the biasing voltage, reverse biasing voltage at this point, between this point and if you consider this point, the gate, the channel and the gate. So as if you have a gate, you have the channel. I'm just showing it in a different way now. So here the voltage is more, here the voltage is less, here it is still less. And this is your junction. So where will the depletion region be more?
Sir, at the center.
Here the depletion region will be more. Here it will be a little bit less and it will be very less here. है ना? समझ में आ रहा है क्या? So this is
Yes,
P
sir.
type, and that is the reason why you get a peculiar shape like this. Very, very important for you to understand this. समझ में आया ये properly? All of you. I am getting only one response.
Yes, sir.
So why do we have this peculiar shape, which is, let us say, which is bigger on this side, drain side? We have the depletion region extending more, whereas on the source side, the depletion region does not extend more. This is the answer to this question. ठीक है? ये बहुत important है. अच्छा. Now let us see the characteristics. This is one thing which is going to be there. So characteristics, or let us say the drain characteristics. JFET. Of course, right now our consideration is with uh, N channel only. So if I draw the characteristics, so drain characteristics means what? Means I have to plot drain current versus, yes, ID versus what? Let us call this as output characteristics. So ID versus what? VDS. So we have VDS here, you have ID here. Okay, up to this point?
Yes, sir.
Now, if you closely see, let me draw the characteristics for you. If it is possible for me to draw, okay, I'll use lines to draw. So I start like this. Okay, this is getting a little bit blurry. Okay, so we have something like this. Okay. So what are these curves against? I mean, by keeping what constant. So what is the input parameter here? ID versus VDS, keeping VGS constant. So what if I'll show you the circuit diagram for plotting the characteristic, for example. So how do you plot the characteristics? You have the JFET. You have the ammeter. This is connected to a power supply. You have this voltmeter here. This is your VDS. So this voltmeter measures VDS. This measures ID, which is flowing like this. Then what do you have here is VGS, and I'm simply measuring VGS with a voltmeter. Remember, this VGS is going to be, oops, the other way around, is going to be negative. All right.
Yes, sir.
It's going to be the circuit for measuring. So what I will do is I'll keep constant VGS, and then I will increase VDS and measure ID, and I'm going to proceed in this manner. So I get a couple of curves, okay, and especially what you see here is VGS equal to 0, something like this. Then VGS equal to -1 volt, VGS equal to -2 volts, and so on and so forth. Okay. So at VGS equal to 0, I have, what do I have? If I go on increasing VDS, it increases ID, or rather, you have non-zero value of ID. Okay? Yes or no? Are you able to understand this?
नहीं सर, ये पॉइंट नहीं आया.
ठीक है, ओके, कोई बात नहीं. ओके, यहाँ पे देखो, मेरा VGS जब 0 था, ये VGS है ना, ये VGS है.
Yes, sir. Yes, sir.
VGS अभी कितना है यहाँ पे? 0 है ना? VGS यहाँ पे कितना है? 0 है.
Yes, sir.
0 है ना? तो कुछ, there will be some current flowing, drain current, because the channel is already there, है ना?
Yes, sir. Yes, sir.
अभी जैसे मैं VGS नेगेटिवली बढ़ाता हूं, so earlier VGS was 0, now I'm going to make VGS equal to -1. इससे क्या होगा? डिप्लीशन रीजन और बढ़ेगा. डिप्लीशन रीजन बढ़ गया तो चैनल का रेजिस्टेंस क्या होगा?
सर वो भी बढ़ जाएगा.
वो भी बढ़ जाएगा. चैनल का रेजिस्टेंस बढ़ जाएगा तो ड्रेन करंट का क्या होगा?
तो थोड़ा कम होगा.
कम होगा. That is what you are looking at here. When VGS was equal to 0, I was having sufficient drain current. When VGS was 0, I was having sufficient drain current. But as I decrease VGS, मेरा ड्रेन करंट का वैल्यू कम हो गया. देखो, और कम हो गया, और कम हो गया. समझ में आ रहा है अभी?
Yes, sir.
So this is what is to be understood. Again, even if I increase VDS, it will not increase ID in a particular region. So if I show you this with a dotted line, इसके बाद even if you increase VDS, ID will not increase. So in this region onwards, we call it as the pinch off region. We call it as a pinch off region. यहाँ तक ही होना है. उसके बाद क्या होगा? Again the same kind of problem will be there. It will be going into a breakdown. जैसे हमने डिस्कस किया था for a bipolar junction transistor. तो यहाँ पे नहीं जाना है. So in this pinch off region, you'll see that ID is absolutely or almost independent of VDS. लेकिन ये रीजन में देखो क्या हो रहा है, ये रीजन में क्या हो रहा है?
सर
If I
VDS के
increase
लिए
VDS,
ID
yes,
एक्सपोनेंशियली
if I
इंक्रीज
increase
कर।
VDS, ID भी बढ़ते जा रहा है. So this is called as ohmic region. Or in simple plain words, when in this region, this device simply acts as a resistor. That's all. और ये जो पॉइंट है इसको बोलते हैं पिंच ऑफ वोल्टेज, VP. Which is having a numerical value at VGS equal to 0. So VGS equal to 0 समझो ये है. Okay, let me put it this way. इसको 0.5 करते हैं, -0.5. ये पॉइंट देखो क्या है. What is
Sir,
that
you are
point?
not visible.
I'm not. Sorry. Hello.
Sir, screen is
सर
not visible.
Screen again. Is that the problem?
Yes, sir.
All of you?
सर अभी तो वापस आ गया है।
आ गया है क्या?
यस सर।
यहाँ पे देखो, ये पॉइंट क्या है? ये पॉइंट ये है जो है, यहाँ पे क्या होता है? आफ्टर दिस पॉइंट ID does not increase with VDS. ये ID फ्लैट हो रहा है यहाँ पे. So after this point, ID becomes independent of VDS. समझ में आ रहा है?
यस सर।
तो इस पॉइंट को बोलते हैं पिंच ऑफ वोल्टेज. We'll see what in more details. Okay? Let us just make a few observations. A, when VGS equal to 0, ये कर्व पे कॉन्सेंट्रेट करते हैं अभी. VGS equal to 0, ये वाला कर्व, ये वाला कर्व. सिर्फ इस पे कॉन्सेंट्रेट करते हैं. Alright, so that it will not be problem. So when VDS equal to 0, what is the value of ID? यानी कहां से शुरू किया मैंने पॉइंट?
सर 0.
Let us concentrate only on this. So I am just drawing it again and again. ये कर्व पे कॉन्सेंट्रेट करो. तो कहां शुरू किया मैंने? ये शुरू किया. ठीक है? That was the point where VDS is equal to 0. So what is going to be the value of ID? यहाँ पे
Sir,
ID
0.
कितना है? ID भी 0. Very good. And voltage between gate and all points in the channel A, B, C जो मैंने बोल रहा था is also equal to 0. वहां पे है ही नहीं ना, करंट ही फ्लो नहीं हो रहा है, तो वोल्टेज A, B, C किधर वोल्टेज ही नहीं है ना? Because ID is
Yes,
not
sir.
flowing at all. Now when VDS is increased, so when VDS is increased, by a small amount, यानी मैं थोड़ा सा यहाँ पे इंक्रीज करता हूँ, अभी यहाँ पे हो, what will happen? A small drain current will start flowing, है ना? Small drain current will start flowing. So small ID flows. Now this even if it is small, it still is going to cause the drop across the channel. So A, B, C point के voltages अभी आने शुरू हो जाएंगे. Now this reverse biases the gate channel junctions by a small amount, causing small depletion regions. ये बात ठीक है up to this point?
Yes, sir.
This ID flows VA small, VA, VB, VC will exist, creating small bias, reverse bias that is, and hence small depletion regions. All right.
Yes, sir.
And this small depletion regions means what? Small penetration. Penetration is not more into the N channel.
Yes, sir.
ठीक है? Is this okay up to this point?
Yes, sir.
So we have negligible effect on the channel resistance. To begin with, we have negligible effect on channel resistance. We have negligible effect on channel resistance. क्यों? Because the depletion regions are small. So there is negligible effect on. I'll just let me remove this so that it is. It's easier for me to. Okay. So small depletion regions will be there, like this, and they will have small effect on the channel resistance. So ID will not be affected much. In fact, what is going to happen is if I go on increasing this voltage between drain and source, this VD, we can call it VDS also. So ये voltage अगर बढ़ाया तो current बढ़ने ही वाला है ना?
Yes, sir.
So depletion region small है, इसकी वजह से it is not going to have large effect on the channel resistance. So current ID increases. So it goes on increasing like this, like this, like this. Okay? That is the reason why you see the curve like this. And in this region, you'll see that it is almost linear. Linear यानी क्या? Linear between what? VDS and ID. ये बीच में straight line जैसे लग रहा है ना ये?
Yes, sir.
और straight line ये किसका characteristic है? Voltage और current straight line है relationship. तो ये किस device का characteristic है?
Conductor.
Resistor. Simple resistor है ना? Voltage, current, straight line.
Yes,
हाँ,
sir.
है ना?
Yes, sir.
Yes, sir. Yes, sir.
So the device is as if it is behaving like a resistor. The device is behaving like a resistor here. आया समझ में?
Yes,
That
sir.
is the reason why it is called as ohmic region. All right. So with further small increase in VDS, drain current increases nearly linearly, and the channel behaves like a resistance of almost constant value. Resistance change नहीं हो रहा है significantly. The channel continues to behave like this as an almost constant resistance until the voltage drop across it becomes large enough. So it becomes until it becomes large enough. So where यहां से देखो यहां ये पॉइंट बहुत इंपॉर्टेंट है ये पॉइंट. तो यहां पे क्या हो रहा है? यहाँ पे current is large enough that it is causing significant voltage drops along the channel, and now you are getting increased depletion region penetration into the channel in this peculiar format. Okay, up to this point?
Yes,
Guys?
sir.
Okay.
Yes, sir.
Now at this point, the channel resistance will be significantly affected. The channel resistance will be significantly affected. कौन से पॉइंट पे? ये पॉइंट पे अगर आता हूं तो channel resistance will be significantly affected. Why? Because the depletion regions are now extending. They keep on extending like this.
Sir, you are not audible.
समझ में आ रहा है क्या? Guys?
सर लास्ट में आपकी आवाज नहीं आई.
Channel resistance will keep on increasing because of this. जब ID increase हो रहा है तो इसके across drop हो रहा है. Because of this drop negative biasing हो रहा है.
सर अभी स्क्रीन नहीं आ रही है.
अब आ रही है क्या?
नो
Yes,
सर.
sir.
Now?
यस
Are you
सर.
able to
Yes,
see
sir.
the screen now?
Yes,
Okay.
sir.
यस सर. यस सर. यस सर. यस सर.
Yes, sir.
तो ये increase हो रहा है. ये increase हो रहा है. But don't forget that your drain current is causing this. Increase in drain current is causing this. है ना? So after this point, something happens. What will happen? These regions, they never touch each other, actually speaking. But increase in this drain resistance is arrested by increase in the channel resistance increase. यानी एक साइड से आप drain current increase कर रहे हो because of VDS, drain current increase कर रहे हो. So increase in drain current. Why? Due to increase in VDS, which causes increase in channel resistance. तो एक पर्टिकुलर पॉइंट के बाद okay, who is responsible for creating the channel for creating this depletion regions? Who is responsible for creating this depletion regions?
Sir, VGS.
No, VGS तो zero है ना भैया.
सर
Sir,
रेजिस्टेंस.
VDS.
It is ID. It is ID which is causing it, no? ID flow रहा है तो VA कुछ होगा, VB कुछ होगा, VC कुछ होगा, है ना? Because as if it is across a resistor, है ना?
Yes, sir.
तो यहाँ पे negative bias जो है, it is created by ID. तो जितना ID ज्यादा, उतना drops ज्यादा और उतना reverse bias ज्यादा. Okay, up to this point?
Yes, sir.
Okay, so ID is causing increase in the depletion region. But because of the increase in the depletion region, the channel resistance increase. समझ में आ रहा है?
Yes, sir.
So ID has caused increase in channel resistance increase. अभी चैनल रेजिस्टेंस इंक्रीज हो गया तो आईडी क्या होगा?
Sir, it will decrease.
Yes. So ID will try to decrease. Or in other words, there won't be any further increase in ID. समझ में आ रहा है कि नहीं आ रहा है?
Yes, sir.
So that is the reason why you are looking at this figure saying that इस point के बाद ID, ये ID है, don't forget that. ID is remaining क्या कर रहा हूं मैं ये? Almost constant. Even if I increase VDS. अरे भाई समझ में आ रहा है कि नहीं आ रहा है?
Yes, sir, आ रहा है.
तो ये पिंच ऑफ रीजन में होता क्या है? ID will remain constant independent of VDS. ये बहुत इंपॉर्टेंट है समझना कि why is the channel not getting pinched off? I mean, even though the effect is called as pinched off, it is not completely cut off. समझ में आ रहा है कि नहीं आ रहा है?
Yes, sir.
So ये पूरा टच कभी होगा ही नहीं इस कॉन्फ़िगरेशन में, ठीक है?
Yes, sir.
Unless you change VGS. That we'll see in the next lecture. So what is it that you have learned today? The new device. ये बहुत इंपॉर्टेंट है ये पिंच ऑफ. ये समझता नहीं लोगों को. I tried to explain it in very simple words. Hopefully you have understood it. Have you
Yes,
really
sir.
understood this?
Yes, sir.
Sure.
Yes, sir.
Okay, please revise this. Again, I am using the same book, Electronic Devices and Circuits by David Bell, for this topic. I think we have already crossed the time limit, so I'll stop over here. I'm going to end the meeting.